We have Jose presenting the opening presentation on OpenMP Offload for the AMD Accelerators. Jose's been working with CNES and other sites in Europe, and he's been instrumental in getting our presentation materials for OpenMP. So with that, I'll go ahead and turn it over to Jose.
Yes, hi. So this morning presentation is about getting started with OpenMP offload applications on AMD accelerators. As agenda, first we'll talk about AMD open source software stack, then expose how to build simple OpenMP offload applications. Next, we'll discuss hybrid MPI plus OpenMP offload applications report, then expose runtime report for performance investigation before summarizing. So, as you know, AMD has developed open source platform for GPU compute. And this platform unlocked the GPU power to accelerate computational tasks. ROCm software is optimized for HPC and AI application and scale from a single node to supercomputer and mega data centers. The open source approach we are using democratize AI and enable innovation, differentiation, and collaboration. So we have multiple support within the ROCm software platform that includes the benchmark operating system, cluster development, cluster deployment, framework support, library, programming model, development toolchain, driver and runtime, and deployment tools. In few slides, we'll focus on our libraries, programming model, and development toolchains. So, as compiler, we have a ROCm compiler collection that is ROCmCC and AOMP. The ROCmCC provides support for both HIP and OpenMP. And the AOMP compiler is developed by AMD OpenMP Research Group for AMD Instinct accelerators. And this compiler is used to prototype new OpenMP features for ROCmCC. What that means is that the compiler is ROCm. Now, if you want to test new feature that we are testing in-house, you can use the AOMP to test that. And when the AOMP feature is mature enough and stable, then you receive the commit in the ROCm, the next release of ROCm compiler. GNU compilers also provide offloading support to AMD GPUs that include OpenMP and OpenCC. And since GCC 11, there is a support for MI100. GCC 13 adds support for MI200 GPU series. And today we have a certain branch that is called OG12 branch that augments the GCC 12 branch with OpenMP and offloading features. So as you know, OpenMP is evolving. GCC tend to support OpenMP, and every day they're adding different kind of features. Another compiler is Siemens compiler that is SOS3 Codebench Lite, and it is free GCC based compiler. This compiler supports all GCC 12 features enriched by OpenMP features from GCC development branch and MDGCN improvements such as support for offloading debugging. This compiler, as GCC is they are still under development. Now, if you are using system AMD HPC system like Lumi or Adastra in France or something like that, you will see additional option. You have additional option that is K-compiler. And this compiler, they provide offloading support to AMD GPUs as well. And this includes OpenMP, HIP, and OpenCC. The full list of OpenMP compiler and tools available via this link we have here. Now, when we talk about compiler, the developer what they want to see is, okay, what is the relationship between the compiler we are talking about and the keyword we will use in our makefile. So if we consider K compilers, for example, you might need to load a module that is called CCE. And if the program, the application is working in C or C++, you might need the keyword CC or capital CC to build your code. If it is a Fortran code, you might need FTN to build it. Now, if you are using AMD ROCm software platform, you have AMD Clang for C code. For C++, we have AMD Clang, AMD Clang++. For Fortran, we have AMD Flang. And in addition to that, we have a heap port. And the heap is basically, in fact, a wrapper for AMD Clang and AMD Clang++. And it also makes sure that it also makes sure to call either AMD Clang or NVCC based on the platform. So heap is used, in fact, when you have portability issues. Now, because we are talking about ROCm software stack, some of these applications a scientist have might be CUDA applications or things like that, but we have additional tool for that one. We just mentioned it, but this talk is focusing on OpenMP parts. We have an application, we have a compiler, but all applications are not they are not just doing a simple computation. Sometimes you might need some math library, some additional library to run the full application. So on CPU, we have math library like FFTW, BLAST. We have a similar thing on GPUs as well. And here, AMD is proposing two kinds of library. We have libraries that start with rock something, that is rock BLAST, rock FFT, rock solver. And we have the other one that is heap something, heap BLAST, heap FFT, heap solvers. So the difference between both is just that if you are targeting, but if your goal is to run your code on both a NVIDIA GPU and AMD one, then you might need consider heap something libraries. Otherwise, use the rock libraries. In addition to this, we have some of these applications that used to do some communications. But when you are scaling, you are considering multi-node run. And you need that additional library to run to take advantage of the scalability. And that is where we have a RICOL, for example. So all these libraries are available in the ROCm package. So this talk will simply focus on simple and hybrid OpenMP offload application building and running on AMD GPUs. So how do we enable OpenMP on AMD hardwares? It is simple. It is like we are running code, OpenMP code in C. So you will need a compiler file that is -f OpenMP. Now, if the compiler we are using here is the Clang, of course we have a compiler keyword that are available AMD Clang, AMD Clang++, or AMD Flang. If we are building our code with GCC, we also need -f OpenMP to enable OpenMP on our target platform. Now, to be able to offload this code on AMD MI200, we will need to add additional flag, and that is that dash offload that hash equal GFS 90A. For MI200 and for MI100, we have a similar flag that, except that the architecture is different, and here we are calling GFS 908. So one thing is to enable OpenMP, the other thing is to enable offloading on the target GPUs, and that is why we need to specify these flags. All these flags are available, all these flags represent the shortcut of what we have in the second column here, and they are available since ROCm 4.5, and you can use it to build your applications easily. As we saw for ROCm, GCC also has different kind of flag. For example, we have -f offload, we have offload options. We need to specify the architecture as well when we consider in GCC. But anyway, offloading target are specified in GCC internal target triplet format. And to check that, you can run the compiler with gcc-v to show the list of offload target under offload target names. So when you run that command, you will see, you go to the section offload target name, and you will see the set of target data available, data supported by the GCC compiler. When considering Cray compilers, we also have the same flag to enable OpenMP. So we need -f OpenMP for C and C++ Fortran, C and C++ code. And for Fortran, we need either -h OMP or -f OpenMP. And again, as for ROCm, here, instead of specifying a flag, we just need to load a module that is called Cray Accelerator AMD GFS 90A when the target machine is MI200. And we have another module that is called Cray Accelerator AMD GFS 908 when the target GPU is MI100. Now, when we are building our application based on Cray compiler, we need to keep something in mind is that Cray compiler has some wrappers, and you might consider using them. So these wrappers are FTN, CC, and capital CC. So they are available as well. You will see some code that are using this wrapper. Other code they use the native name Cray CC, Cray FTN. So the shortcut is available as well. Here we have a reduction example, and as you can see, inside it's a small code, it's a small codelet, and we are creating a data region here, OpenMP target data map, where we are mapping data A, buffer A and B from host to GPUs. Next, before computing our loop in parallel, we copy the sum from and to. While we copy sum from CPU to GPUs, and after running this code, the sum value will be copied from GPU to CPU. That's why we have to and from. And this computation, within this simple algorithm, we are doing a kind of reduction on some variable. So how do we build this code? It is simple. We call the compiler, we activate our flag for OpenMP support, and the flag that enable offloading on GPUs, and that's it. Concerning Fortran and OpenMP offloading, the OMP, we have the OMP compiler that is available with Lang. You can use the GCC compiler as well with gfortran, but remember, many features are still being added to Fortran's compilers, and use the latest compiler versions, and expect feature to be added with every release. Here is a simple example of Fortran OpenMP offloading. And as you can see, we have our pragmatic distribute map to map. So we are creating a parallel region here, and we are mapping the array. We are copying this array from host to GPUs. And we can see here that we have another buffer which we need to bring back. We copy from CPU to GPU and bring result back from GPU to CPU again. And we have some private variable. Within this region, we have the compute loop in parallel on GPU section. And here you can see that we are performing a reduction on sum 2. The end parallel do represents the end of this compute region, and the end target distribute represents the end of parallel code region. And we build this code the same way we built the previous code. So here we are using the long format of this flag -offload -at equal GFS 9A. So it is exactly the same thing we are doing here to build this code. On this page, we are sharing some a simple unified share memory codes. And here you can see that, okay, before starting, we used to set the pragma and tell our compiler that we want unified share memories. Now, depending on the way you allocate the buffer, you might need the device ID or not. So device ID, when you are using OpenMP target allocation to do your allocation, your memory allocation, you might need the device ID. Otherwise, you can use malloc, simple malloc, or you can use POSIX mem align to align this buffer as soon as you create them. So depending on the type of allocation you need, you might need to free this buffer at the end of the execution. So it can be OpenMP target free or it can be free, simple. And within this, we have our compute loop with offloading pragma available. Here also to build this code, it is simple. It is exactly as previous code. We call AMD client, we enable OpenMP, we set the target architecture, and that's it. The example we saw a few seconds ago is a simple. It is a simple one. It is not so complicated, but some of these examples, some of these applications, or some of real-life applications that contain, in addition to simple algorithm, we will see some math library call. What do you do? What do we do when there is a math library call in our application? How do we build this kind of application? The idea is simple: is that if you have a math library, something like a Rock Blast, Rock Allusion, heap solver, or any kind of library within the ROCm software package, you will need to specify that. So for example, we are calling -l heap blast, and you need to add a -l AMD heap 64. If it is Rock FFT, your code is computing a Rock FFT, it is exactly the same thing. -l Rock FFT plus AMD heap 64. So here we have some, for example, a GCC, a Fortran code built using gfortran, and and this code is calling Rock FFT. The other one is calling dgem. And based on this, so we link this code to build this code. We link with corresponding library in the ROCm software stack. Application are multi-order. So we have simple application and we have a hybrid application as well. So what kind of support, offloading support do we have for hybrid API plus OpenMP applications? As you know, most popular HPC applications, they rely on multi-GPUs, MPI programming model to scale their workloads. And MPI is widely used to scale multiple nodes in HPC applications. So to be able to do that, ROCm enable various technologies to facilitate reporting of your application on clusters by allowing direct use of GPU pointers in MPI call and enabling ROCm-aware MPI library to deliver optimal performance for both intra-node and inter-node GPU to GPU communications. So you run your codes. If it is a simple code, you can run it on one GPU. But when you are, as soon as you start targeting multi-GPU, every in the single node, or multi-GPU in multiple nodes, you might need a ROCm-aware MPI technique. And to be able to do that, you need to activate ROCm need to be to have a certain feature available to make this feature available to the developers. And we'll see that in few slides, how what can be done to make a MPI library ROCm aware. Now, for some of these applications, you might need MPI binding to get great performance. It is not always the case, but some applications require that in addition to ROCm aware MPI libraries. Multi-GPU support mean that we have different kind of GPUs. So to check that if you have a different GPUs on your target on your machine, you can use a command line, the same command line like -i. So here, for example, show that okay, we have 8 GPUs on the machine we are using here. So because of these multiple GPUs, then we can run our application using all these GPUs. Now, in a context of hybrid MPI OpenMP applications, which change do you need to make on your applications? For example, if we are using Cray compiler, we need additional module that is called Cray MPish. In addition to the CCE module. So the flag is still the same, the compiler keyword is still the same. If we are building our code using AMD ROCm, we will need the OpenMP or OpenMPI. And here, depending on the code we have, if it is CC, we will need the keyword MPI CC in our makefile to build our applications. If it is C++, we might need MPI capital CC, MPI C++, or MPI CXS. Same thing for Fortran, we might need MPI Fort, MPI F77, or F90. Now, one interesting thing is that if we look at Cray compiler, when we load this module Cray MPish, we have the possibility. First, when we load the module CCE, in addition to this, to Cray CC, Cray capital CC or KFT, we have the wrappers available. Now, when we load the Cray MPish, the developer, in fact, you don't need to change any compiler compared to the ROCm, for example, where we need to use MPI CC or something like that. And one interesting feature is that MPI header files are automatically linked to your program when using Cray compiler wrappers. Only wrappers. When you are using this, they are automatically linked. But when you are using the full keyword, there is no guarantee that you will get that. For ROCm package, the other way to build MPI application is that you can directly use Clang or Frank compilers instead of using MPI CC, MPI C++ or MPI CX, all this stuff. You can directly build it based on Clang or Frank compilers. And in that situation, then you might need to add a specific flag that is called that -l MPI and include necessary file from the MPish directory. So it depends on the developer choice what he wants, but depending on the application of the developer choice, you might need some to add additional header file or additional library if necessary. Here we have an example. That is an example of that is a triad OpenMP triad application, and it is a hybrid MPI OpenMP offload one that we will try to run on a certain GPUs. So as you can see here, we have initiate our MPI, and we start with our MPI initiation. We have our code, and in starting from here, we create a data region. We map our buffer X, Y, and Z. So data will be copied from cluster to GPUs. Now, instead of doing like this, we can use the other way because the S is just initialized by 0. So we can directly allocate X on GPUs. So next, we have our compute loop here with the necessary pragma to offload this piece of code on GPUs. And then we finish by target exit data to close our data region. So we collect a certain number of information based on the timing information, and then we have a reduction at the end, MPI reduction, we complete the bandwidth and finalize our MPI call. So as you can see here, it's a mix of MPI and OpenMP. OpenMP, we have both available inside this code. This is an example of a hybrid MPI OpenMP code that you can see in real life. So how do we build this code? It is simple to build this. We just use the Clang as it is. We add our -L MPI library, -F OpenMP to enable OpenMP, and to be able to offload, we add the architecture offload act equal GFS 19. So we are using MI200 to build these applications. After building, you run the application. If we consider a 16 process, you can run it like this directly. But you can also run this on a single or multiple GPUs by specifying if your goal is to use a specific GPU, you can use it through a feasible device variable. So you specify that and you can run the same code without any problem. The GPU we are using here, the machine we are using here has 8 GPUs. So on this example, we are using 4 GPUs. The GPU number 2, 4, 5, 7. So we specify that we need this GPU to run this piece of code. But remember, when you run it like this, all visible devices are visible the visible devices are visible to all MPI rank. Now, you might need to ask yourself, if it is really what you want. So the other way, and it is the general one, the other way to run this code is to use slurm features. That is the method that is based on slurm. And how do you build this? Let's consider this two-step run. So we have two scripts. One script that is run with S-bash command line to launch the applications, and the other script contain S-bash parameters and the call to srun command. So if you look at the high-level screen, you will see what you will see there is basically we load all the necessary modules. You can build your application there, and then the S-bash, we are working on a certain partition, we are working on a certain node. So you will have all the necessary expression to allocate a node, estimate the job. And the job description is within this file, and this is how it looks like in general. So you specify all SBAS options that are necessary to you, and you load necessary module that your application needs, and then you call srun plus the application and any argument, or you can use MPI run as well to run it. So we have an application, we know how to build it, we know how to execute it on GPU, but it is not sufficient it's not sufficient to get great performance. So what do we need? We need ROCm aware MPI in the context of hybrid MPI OpenMP applications. So MPI support for ROCm, we have several of them. We have OpenMPI, MPISH, MVPISH2, and MPI implementation can be made ROCm aware by compiling them with UCS, that's Unified Communication Cross Framework. And one exception is MVPISH2, it directly supports AMD GPUs without using UCS. So because we are communicating, we need to communicate between GPUs. We need a certain way, instead of going through from GPU to host and then go back to another GPUs, we need a certain way to directly communicate between both two GPUs or multiple GPUs. And that is why we need this ROCm aware MPI support. And UCS is ROCm aware, and ROCm technology are used directly to implement various network operation primitives. So ROCm today has all features available, all features have different kind of features that support UCS without any problem. So the same thing to do is to build your MPI library with UCS support, and that's it. In addition to the ROCm aware MPI, some applications, as we said, might need binding to get great performance. So when you are scaling, you need to do the correct mapping between all CPU, GPUs, the memory if they are separate. So they are separated. So you need sometimes you might need some binding technology to get great performance in addition to the ROCm aware MPI capabilities. And in your ROCm, the ROCm you have on your hardware today have a default binding script that are there, and you can access it. It's simple. If you load any ROCm module, you can go to this path script location. It is available there. That is called GPU runs. So every release of a ROCm has this script available there. You can use it. You can change it. You can modify it. You can copy or change in the way that it works for your applications. The goal of this script is to help. In fact, the way it works, it is to help distributing GPUs and the compute unit across multi-rank of API jobs. So it is a wrapper script to execute a GPU application, including OpenMP once, and the script launch the application with a Linux start set. Is set environment variable ROCm visible device, as we saw in previously in few slides back. Is set OMP X target team slot to the number of compute unit available to the process, and if necessary, it set HSA compute unit mask. So the script is available there, and you can easily use it to do the binding, CPU GPU binding. How do you use it? So to use this script with your application, it is simple. Here is an example of usage. You just call the script GPU run your application and necessary argument to run your application. Combining with MPI, you can do MPI run the number of process plus GPU run and your application plus argument. This kind of run, we used to do that when we have HPC application, but it also works when we have AI applications as well. Because AI application, most of the time, they have scaling issue. You need to run this, you want to run it on multiple nodes simultaneously. So in a context like that, mapping or binding might be necessary, depending on the application you have. So we know how to build our hybrid applications. We know how to run it. We know what we need as MPI, if it should be ROCm aware or not. And we also know the binding process, but it is still not sufficient. We need to know what the code, when we are running this code, what happened, what is going on, what is the runtime report. We need this information in order to further optimize our applications. So to enable optimization reports, we need to add a flag that's G. When considering a compiler like AMD OMP, in addition to the .g, we need a specific variable libomp kernel trace. We can set that to 1 or 2 just to enable tracing. So when we are running the application, we need to understand the performance information we are seeing, how it will look like, what is inside the performance we got, or how the code is running on GPU. We need some of this information to further optimize the application. And that's why we need to export a variable like libomp target kernel trace equal 1 or 2. When you use =1, for example, it will show you the kernel name at assembly level, the number of teams, the number of thread limit, register users of your kernels. When you use this variable =2, you will get the same information plus data transfer information and map pointers, including per kernel timing information as well. So basically, setting this variable enable profiling directly when executing your application. For compiler that use a heap backend, so if we have meeting compiler, for example, create use heap backend sometimes. So for this compiler, you can set this variable AMD log level equals 0 to 4 to get debug information to know what the compiler is doing in the backend of your application to have to collect all this data in order to further optimize your code. You can use this variable as well. Now, this variable create ACC debug is specific to create compilers, and you can set that to 1, 2, 3, and it will give you another report as well. Now, one thing to keep in mind is that the outputs you are getting from by setting these variables, they are different. But we focus on libmp kernel trace just because this variable, in fact, is good for both compiler regression tracking and quick performance gap analysis. When you build your code, you have different kind of compiler, you build your code, you will see that, okay, if you observe using one compiler, you are getting better performance than the other one, then you might need to profile your application in both contexts to see what is going on in the backend. So here is an example. Let's consider this FastPay application. It is a simple code that we are offloading on GPUs. The basic way to collect the execution time is to have a start before calling the kernel, a stop, and you collect all you collect set of execution time, you compute the average, and that's it. But the execution time that is reported when you do something like that comprise multiple elements. How can we access what is going on there? What is the cost of every step within these applications? Within the time that is reported here. So to access this information, first let's export libmp target kernel trace equal 1 and run this application again. So when you run it under the OMP kernel equal 1, what you get is that you get the device ID, the GPU ID. You can get also the constant, the work group size that your application is using, the number of teams, the number of threads, the LDS of usage, Scala GPA count, the VGPA count, you have a SGPA spill count again, and VGPA spill count as well, plus the trip count. In addition to this, you have the codes, your kernel name at assembly level. So by using just this libmp kernel, by setting libmp kernel, libmp target kernel trace equal 1, we have access to certain binary information and how our code is executed. Now, when we use libmp kernel trace equal 2, you can clearly see that the output is different and it is huge compared to the one we got previously. This metric that we are seeing here represents, in fact, the communication between host and device with the time every metric, what is the cost, the time associated, the cost associated to every metric while running this piece of code. So, for example, to load a single binary, it took 1093 microseconds. So you have all this information available. If you look at clearly, you analyze this information, you can clearly see that here, for example, we have data allocation, data summation, asynchronous data submission. We have it twice. We have a targeting region execution. That is the run when we run the piece of code. We have data retrieve section, we have synchronization section, and then we have data delete. So the output we are getting with the libmp kernel target include, in fact, data transfer time, invocation time, and per kernel transformation, per kernel timing information. So why are we having two? For example, if I consider this, why do we have twice this information? We have twice just because, if you remember, our codelet is like this, and we are mapping X and Y. So we are moving data from host to device. So we have X and Y. So we have two buffers that we are moving. And that is why you have two sets: data allocation, one, data submission, another data allocation and data submission. So these represent the two buffers. And that is the cost we are paying while moving data from host to GPUs. At the end of the execution, data are deleted, and we are paying for that as well. So if you see, you look at this clearly, you will see that, in fact, it is like we want to run our application, but we need to pay something. And that is what we call offload tasks. So you have different kind of the pre-coded execution time. You can get it via this metric, run targeting, and it's just 245. But before that, we need to pay something, and after that as well. So all these represent, in fact, offload tasks. So that is why these metrics, in fact, they are useful for performance modeling, poor performance investigation, or performance gap analysis. You can use this metric for that. They will help you a lot. So here we are just defining some of these communication between host and device. These metrics are there. It is just a definition. One thing I need to pay attention to is that you can see that data submission can be done asynchronously. So this will reduce the overall, this will help boosting the performance, in fact. If it is not asynchronous, the execution time will be huge compared to asynchronous activities. So to illustrate this, let's go through a few examples. You know, there are some techniques are used to minimize data transfers. For example, you can use target enter data or target exit data directive when variable are used when your variable are used by multi-target constraints. Another way to minimize data transfer is, for example, to choose the right map type for a map variable, read only, write, or alloc. If it is just allocation, please use allocation, don't use map2. Just write map alloc, for example. Here, another thing is it is recommended to not map read only scalar. If you mark read-only scalar, what will happen is that you will see data allocation, another data allocation plus data submission, but it is just a simple scalar. So as we saw previously, data allocation and data submission, they have a cost. So if you map a scalar, then you will pay for that, and this can be bad for the performance of your codelet or piece of code. So instead of doing that, you might consider using first private or not. Don't use anything at all and to work. So these are some techniques to minimize data transfer. Now, how do you check the impact of this change of your kernel? If you build your code, you have your offloaded code available and you want to reduce the data, minimize data transfer, and you use one of these techniques, how do we check the impact of the change of your kernel? It is simple. You export libmp target kernel trace equal to. You run the kernel before and after this change, and then you compare generated profile, and you will see if there is any metric that is taking more time than that is taking or that has been reduced between both versions. You will see if you compare both generative profile, you will clearly see what is going on. Another place where it is interesting to use this kind of profiling is when we try to reduce memory allocation. For example, as we said in the previous slide, map2 is not always the most efficient way to allocate memory for a variable. So if it is map alert, use map alert, or place the declaration of the array between declare target and end target. So let's consider, for example, this array, and let's say that it is a temporary array. If it is a temporary array that we move to GPUs, depending on what is inside the array, you might need to replace map2 by just map alloc. Or you can just place this array within declare target and end target. And here again, how do we check the impact of this change on your kernel? It is simple. You export libmp kernel trace equal to, you run the kernel before and after this change, and then compare generative profile. So to conclude this talk, as of today, we have 4 compilers to effectively offload a kernel on AMD GPUs. That include AMD ROCm. We have Cray, GNU, Siemens compilers. Many libraries are available. Use them where possible. And on your target on Lumi today or on Adastra, you can use module avail command to check available libraries. You can use module show to see the installation path if needed. In certain situations, some module may not interact well with compilers. When this happens, please you just need to provide both header and library path and certain library manually. But the key point here is that you need to learn from the compiler help. You need to learn from the compiler verbose outputs, learn from the debug information, and learn from SPatch as well options. Thank you. Any questions?
So we have one question in the chat from Tomaso. Can a single MPI process be run on one GPU, i.e. 2 GCDs, or should I always use 2 MPI tasks to exploit the full GPU?
Could you repeat that question, please?
Can a single MPI process be run on one GPU, i.e. 2 GCDs, or should I always use 2 MPI tasks to exploit the full GPU?
Okay. In fact, you can, it depends. You can do both. The thing is, if you have one MPI task, you can just use a single GPU without any problem. But if the goal is to have multi-process, you can schedule one MPI task on every GPU. So it depends on what the application is doing, and it depends also on what you, the developer, what you want.
So
Okay, thank you. So you mean that can be set through the environment?